Algebra 2, lesson 5.1 is called matching up data. All right, so our learning goal here is I can describe how to transform a graph. All right, very generic learning goal, but something that we need to be able to do. All right. All right, so before we go on, this isn't part of our book, but I think this will be helpful. These are all the transformation rules that we're going to use basically. So I want you to go ahead and pause this video, and I want you to, right here, I want you to copy these transformation rules into your book or your notebook or wherever you know you'll be able to find them. Okay, so go ahead, pause the video. Um, but basically, we're gonna need to refer back to these quite frequently. So vertical transformation, vertical translation, horizontal translation, vertical scaling, horizontal scaling, and then both reflections across both axes. All right, go ahead, pause the video, and we'll come back to those as we use them. All right, so what do you notice? What do you wonder? So let's make a little list here. Start out with notice. Um, function is decreasing. I notice it is a scatter plot. I notice it looks linear or exponential. Okay, hard to tell with this data. We don't really have a lot of it. So, I mean, I could make an argument that it looks like if I drew my best fit line, kind of looks like a line there. But I could also make the argument that it looks like an exponential decay function. So if I were to draw like a curved decay function, kind of looks like that as well. So not really sure on that. That might maybe be more of a wonder than a notice. But back to here. Notice, here's a wonder. I wonder if it's exponential or linear. I wonder what is the function of best fit. I wonder why is there a big gap from 3 to 5.5 roughly. Okay. So, a lot of different things here that we don't know about this. Oh, here's a notice. I guess I could put another one here. I noticed that the y-axis represents temperature and x-axis represents hours. Okay, that's a big thing to notice there. But a lot of stuff there that we don't know. Just kind of talking about vocabulary, talking about linear functions versus exponential, talking about scatter plots, best fit lines, and also really important to look and see that there is this giant gap here. And it's, probably not the best data that we would have. Okay. So the next thing here, we have a scatter plot, and it's plotted, I think, in your book. I have it all plotted here on the graph. And basically, they plotted a bunch of different temperatures. The y-axis is temperature. If you look here, and the x-axis is time in hours. After the soda was left outside. So there's two functions there. There's f of h, which if you look over here on the graph, f of h is right here. So we'll call that the green graph, because if you look at the thing next to the little color mark next to the function, it's green. And then the other one is purple. So let me find a purple. All right, the purple function right here, and it's on the graph as a purple graph, okay? So let's take a look here. Excuse me. All right, so which function better fits the shape of the data? Explain your reasoning. So most of you would probably say, I don't know, from my experience, most people say the green graph. So most people say f of h. And the reasoning is it is closer to the data basically everywhere. Okay, so like when I say closer to the data, if I look here, like let's just pick a random point here. So like this point right here, if you look here, the green is definitely closer than the purple. And then you pick another point here and like let's look right there. The green is definitely closer, whoops, closer than the purple. Okay, pretty much everywhere. Um, so most people say f of h is a better fit. Okay. Um, so use the applet to zoom out on the graphs. Does this change your opinion about which function fits better? So I'm not going to really zoom in or zoom out. But what I am going to do is I'm going to do this. I'm going to trace the graph, trace the purple graph as best I can. All right, there. No, that's not very good. Let me redo this. Let me use a highlighter. Might be a little bit better. It's a little bit better. All right, so there's my purple graph. All right, and what I'm going to do is if I move this thing left or right, okay, you might see if I translate it, I could probably get it to fit pretty darn close to all the data, even better than the green one. Okay, so that's all I wanted to do there for number two. Number three, where do you see the 45 in the expression for each function of the graph? Where do you see the 45? So here we got a 45. If you look up here, we got the 45 right here. We got the 45 right here. And I would say it's probably the horizontal asymptote if you were to look at it. So 45 would be right here. Whoops. So as I look there, looks like horizontal asymptote for both of these. Now the purple one, it definitely levels off a lot sooner. But if you look at the green, if I were to extend this graph, I think it's going to eventually level off. Okay. So my answer to that question is where to see the 45? It appears to be the horizontal asymptote. Okay, number four. For the function you thought didn't fit the shape of the data as well, how would you change it to fit better? So I would I would translate it a little bit. I would move it to the right. I'm not really sure how much. We have to kind of play with it a little bit more. And if you had your textbook, you could use some tracing paper. That would be a really good way to kind of do it. But here, let me just, oops. right, so I would move it right. Man, I don't know. Move it. Probably just move it up. In all honesty, move it up. Move it up 20 or 10. Move it up 10 probably. So I probably don't even need to move it to the right. Let's just say move up 10 or so. Okay. Now instead of move, I might be better off to use the word math word, which would be translate. Right. So basically what we wanted you to do on that is to realize that, one function might appear to be better fit, but the other one might actually fit the shape a little bit better after I do a little translation and stuff like that. All right. So basically, what I've done here is I've given both cards. All we have to do is take turns describing the transformation of the graph um, for to the other graph. So basically, we're going to start with the first one, 1A, and we're going to go to 1B. Okay, so we're going to go from this graph to this graph. Okay, so we're going to have to describe the transformation. So the first one, it looks like I just translated up 3. Right, and if you take a look here, let's see if I could trace it and do that. Here's my original. If I move it up 1, 2, 3, so that vertex goes up 3. So does everything. Everything really goes up 3. It looks like I'm going to get the same graph. Okay. So then we go here to the next one. And what you really want to do is you want to find a point that you know for sure. So, like, I'm going to look at this point right there because that's negative 1, 0. It looks like it just moved to the right, 1. Okay, it looks like that point ends up right there. So I'm going to say I'm going to translate right 1. Then we're going to go over here. And I think a good point to reference would probably be right there in the middle. And we see I go from, really it's at 0, 4 to negative 1, 2. So that one looks like it's going to go down to and left 1. Because this point started at, I can show you here, it started at 0, 4. And then that point ended up at negative 1, 2. So you can see your y's decreased by 2, so we went down 2, and my x decreased by 1, so I went left 1. All right, let's go here. So again, we're going from here to there. Really, it's a flip. So you probably remember from geometry, that's going to be a reflection. This one is going to be a reflection across the y-axis. It looks totally like a nice little flip here. If I were to, and you can kind of tell by, like, if I find a point here, like this point, for instance, is 2, 7. If I change the x, I have negative 2, 7. So you look here, this is 2, 7. And you look here, this is negative 2, 7. So when I reflect across the x-axis, the y-axis, the x sign changes. Okay, and then you got another one. Well, I know it's not quite there, but let's call that 1, 3. It's a little off, but we'll just call it 1, 3. If I look here, I got negative 1, 3 right there. Okay, so you see that the x's change. All right, now the next one is a little trickier because it gets compressed in. Okay, See how everything gets squeezed in. If I find a point here, like this point right here, I'm at like about 1.5, and then all of a sudden I'm at like 3/4. So this one looks like it's a horizontal scale by 1/2. Okay, now sometimes they say horizontal compression. You might see that word too. Okay, horizontal compression by 1/2. Either one would be fine. And then the next one, it's kind of the same thing. We're getting wider this time. So my function is going to be getting wider to go from this to that. And I guess I should have an arrow here. Trying to restart there. But this one here is going to be a horizontal scaling. Now, how much do you scale by? Well, let's find a point. So this point here was 1, 1, and it looks like that moved to the right too. So you're at 1, 1, and then we ended up at 2, 1. So you see that the x is doubled. So we're going to call that a horizontal scaling by 2. And instead of scaling, you might see the word stretch. Okay, but they basically mean the same thing. All right, so describe how to transform each graph to fit the point. So this is our lesson synthesis. So first one, here's my line. It looks like I'm gonna pick a point like right there and put my cursor right there. It looks like I just gotta move right 1. Okay, so for that one, translate right 1. Pretty easy. Next one, this one looks like, if you look here, and I'll show you here on my graph, I look at this point right here, and then let me use a different color. You can't really see that very well. You got this point right here, and then I go to the right 1 and up 3, kind of like the same here. This is to the right 1 and then up 3 to go there. So it looks like I got to move this point here, right 1, and then up, oh, I'm sorry, up 2. Yeah, I got to go right 1 and up 2. Nope, I'm sorry. Yeah, that's right. I need to get that point where I started to the first blue point. So right 1, up 2. Right, and I'll trace it and I'll show you here. So, oh, darn it. Try it again. All right, and if I pick this point, I move it right 1 and up 2. Pretty close. All right, looks like I'm right through those points. Obviously, my picture was a little shaky, but there it is. Okay, and then the next one. So let's take a look at our graph here. So these are right 1, up 3. So I got to find 2 points that are equally spaced like that. So I think I'm going to choose this point and this point. I go to the right 1 and up 3. So I need to move, basically I need to move this point, I'll use the red here, to that point. So I got to go right 2 and up 2. Really, and either one, or I can move this point to that point. Same thing, right 2 and up 2. All right, so let me highlight this and we'll try it. All right, so I'm going to move this point right 2, up 2, and it looks like it went through. Okay, so which graph fits the data best? I would say after we transform them, all three fit perfectly. Okay. Imagine a situation where each graph, linear, quadratic, and exponential, would be the best choice to model the relationship. So obviously, I guess I didn't mention it, but I guess I probably should. This is obviously linear because it's a line. This is quadratic because it's a parabola. And this is exponential. Okay. Linear. Well, you're going to need to have constant rate of change. So I would say maybe something like adding the same amount of money to a piggy bank each month. Okay, so you're going to have a straight line is going to rise and run the same amount. Quadratic. Oh, I would say maybe a ball, right? Because when you kick a ball, it's going to take a parabolic shape. And then exponential, I would say, investing money into an account that grows exponentially. Okay, compounded interest, those we all know go up. All right, when we fit a curve to data points, will the curve always go precisely through all points? All right, that's a pretty easy one. No, scatter plots are not necessarily always a perfect fit for a function. We usually try to find the function of best fit. All right, so the goal today was I can describe how a graph is transformed. We really didn't do much with reflections. We did a tiny bit, with scaling, did a lot more with translations. So hopefully we're pretty good with all of that. I didn't really get into the function rules that we had at the beginning, but I wanted to drop those there for you because we're going to use them coming into the next couple lessons. All right, so the last thing is this cooldown. There are many ways to translate the graph so it goes through the point 1, 2, describe 2. Okay, so let's see here. Find a point, and the key word here is it says translate. Okay, so I originally looked at it and I wanted to do a reflection. I wanted to just reflect this thing right across the y-axis, but it says translate. So I have to slide it. So basically pick any point, maybe start with this one. And let's see here, I'm going to translate. If I want to move that point to there, I'm going to go right 1, up 1. Translate right 1, up 1. And if I had a different point, like maybe this point, All I'd have to do is translate it right too. All right, I wouldn't have to move it up or down. I even do a third one just for fun here. If I had that point, I would move that right 3 down 2. All right, all of those would go through that point. Okay. All right, so many different ways. All right, thanks for watching.